Hi everyone, I'm Greg Stitt, and in this talk I'll be giving a tutorial on the Quartus timing analyzer to demonstrate how to perform timing optimization of a simple circuit. First, let's quickly review the important details from the previous presentations. When performing timing optimization, our goal is to ensure that timing constraints are met for all paths between all flip-flops. Now, a timing constraint is met when the sum of the cell and interconnect delays is less than or equal to the sum of the clock period and the clock skew minus the flip-flop setup time. Or a simpler way of thinking about this is that we want to ensure that the time between flip-flops is less than or equal to a specific deadline. Now, to demonstrate timing optimization with the Quartus timing analyzer, I'll be using a simple adder tree circuit that is provided in the repository at the URL shown on the slide. Before I jump into using the timing analyzer, I first need to explain the naming conventions used in Quartus, which are slightly different than what I've presented previously. So the Quartus timing analyzer compares two different times, a data arrival time and the data required time. Data arrival time is the time it takes for the source flip-flop's output to arrive at the destination flip-flop, which is similar to my definition of the time between flip-flops. The data required time is similar to what I previously called the deadline. It is essentially the time when the output of the source flip-flop is required to have arrived at the destination flip-flop. So let's take a look now and see how these times are slightly different than my previous definitions. So let's look at the data arrival time first. The Quartus documentation defines this time as the summation of the launch edge, the source clock delay, the micro clock to output delay, and the register to register delay. This launch edge is just the time of the rising clock edge for the source flip-flop. You can think of it as the source launching a signal to the destination. Now this value is usually just going to be 0. The source clock delay is the propagation delay of the clock source to the source flip-flop. Basically, Quartus separates the clock skew into components for the source and destination flip-flops. So here, the source clock delay is just the skew component for the source flip-flop. The micro clock to output delay is really just an elaborate name for what I previously called the clock to cue delay in the previous presentations. This is really just the time it takes after a rising clock edge for the flip-flop's output to change. And the micro part of the name is really a misnomer because these times for modern FPGAs are under a nanosecond, so they are much faster than the micro that the name would suggest. The register to register delay is basically the same as my definition of the time between flip-flops, except my definition included this micro clock to output, or what I called the clock to cue. Note that this register to register name is also a little misleading because we need to measure the delay between pairs of individual flip-flops, not just pairs of registers. So two registers can have significantly different delays between different pairs of flip-flops because of different logic delays, because of different interconnect delays, and so we really want to focus on flip-flops. But I will stick with Intel's naming convention because that's what you will see in their documentation. Now we'll look at the data required time. This time is the sum of the latch edge and the destination clock delay minus the micro setup time of the flip-flop. Again, ignore the micro part of that name. Setup times are under 1 nanosecond, so I'll just refer to them as the setup time, but you need to be aware of the micro naming convention since that is what shows up in the timing analyzer. The latch edge is the time of the rising clock edge for the destination flip-flop. Again, the latch terminology can be a little confusing because there isn't actually a latch, so here the latch is referring to the destination flip-flop. Assuming the launch edge that we saw on the previous slide was 0 nanoseconds, then the latch edge is just the clock period. But in any case, the latch edge will be the time of the launch edge plus the clock period because we are giving the source flip-flop one cycle to send data to the destination flip-flop. Now, the destination clock delay is the propagation delay from the clock source to the destination flip-flop. So, similar to what we saw with the source clock delay, the destination clock delay is another component of the clock skew, but this time for the destination flip-flop instead of the source flip-flop. So this slide explains the differences between my definitions and the Intel definitions. Technically, both are describing the exact same constraints, just in different ways. First, the data required time is very similar to my previous definition of the deadline. In fact, both represent a deadline of when a signal must reach the destination flip-flop. However, my deadline definition simply uses the clock skew instead of just using the destination clock delay. Now, the skew is just the difference between the destination clock delay and the source clock delay. So basically, I just move both components of the clock skew into the deadline equation, whereas the Intel timing analyzer explicitly separates the components of the skew. Now, the data arrival time is similar to my definition of the time between flip-flops, but with the source clock delay included. Note that the clock to queue, or the micro clock to output time, as Intel called it, is included in my definition of the time between flip-flops, whereas in Intel's definition, it keeps it separate. In any case, the main point remains the same in either definition. We want to ensure that both of the following conditions are true for all paths between all flip-flops. We can either think of it as keeping the data arrival time less than or equal to the data required time, if we are using the Intel terminology, or if we're using my previous terminology, we want to keep the time between flip-flops less than or equal to the deadline. Alright, so let's take a look at the example that we will be optimizing. The circuit we're going to use is a simple adder tree that takes 8 inputs, where each input has a width that is specified by a Verilog parameter. The circuit then adds those 8 inputs using 3 rows of adders to produce a final sum that has the same width as the inputs, so we're basically ignoring all overflow. In addition to the adder tree, the circuit also has registered inputs and outputs, which are necessary for timing analysis because to analyze clock frequencies, you have to analyze pairs of source and destination flip-flops. So taking a quick look at the code, we can see how this circuit gets synthesized. The code uses an always flip-flop block that assigns the input array to an internal logic array, which creates registers for the inputs because it is done on a rising clock edge. Similarly, we have the sum output becoming a register because it is also assigned on a rising clock edge. This slide looks at another part of the code that includes a second always block that we use for the combinational logic in this example, which in this case is just all of the adders. So if you look at the block, the first 4 lines add the 4 pairs of registered inputs. The next 2 lines create the second row of adders by adding the sums of the first row, and then the final line creates the final adder that adds the 2 outputs from the second row of adders. Now, before we start with the timing analysis, there are some things we first have to do in Quartus. These are already done for you in the project provided in the repository, but it is important to understand for when you create your own new projects. First, before timing analysis, you have to set a clock constraint, otherwise the timing analyzer doesn't have a deadline to work with. So I'll explain the basics on this slide, but make sure to read the Quartus documentation for the full details of how you can specify constraints. Constraints are specified in SDC files, which you can also specify using the Quartus GUI, but Quartus will just store those in an SDC file anyways, so sometimes it's just more convenient to specify it directly in the SDC file yourself. For this example, the project includes an addtree.sdc file. Within that file, you can find a create clock command that defines the clock constraint that we're going to be using. So the name flag for this command just gives the clock constraint a name within Quartus. This can be anything you want. I just happen to make it the same name as the clock in my code, but it doesn't have to be. The period flag specifies the clock period in nanoseconds. So here, this clock constraint has a 5 nanosecond period, which means we want a 200 megahertz clock. The waveform flag lets you specify the rising and falling edge times so that you can control the duty cycle, which in this case is 50%. The getPorts command is what connects this constraint to some signal in your code. In this case, we specify clock or CLK because that was the name of the clock signal that we used in the System Verilog module that we are working with. So this name has to match the name of your clock signal in your code. One more Quartus issue you need to be aware of is that by default, Quartus will connect all module I/O to FPGA pins. Now normally, if you want to connect the I/O to specific pins, you also do that with constraints. However, in this case, we are just analyzing the timing of a module by itself, so we really don't want the I/O connected to pins at all. The reason for this is that modules are normally connected to other nearby modules, so by mapping the module I/O to pins, you could be creating excessively long delays that test an unrealistic use case of the module. In addition, it is common for module I/O to exceed the total number of pins on the FPGA, in which case it won't even compile. To solve these problems, Quartus allows module I/O to be mapped to virtual pins, which are just internal FPGA resources, generally lookup tables that surround your module, that act as pins for the purpose of timing analysis. To specify virtual pins, you include this information in your QSF file, which for this example is the addtree.qsf. Or alternatively, you can also specify it using the assignment editor in Quartus, but that will just directly edit the QSF file, so do it whichever way is more convenient for you. Generally, we want to apply virtual pins to all module I/O except the clock and reset. So in this case, we have two instances of this set instance assignment command, which turns on virtual pins for the signal specified after the to flag. So in this case, the first command enables virtual pins for the inputs array, and the second command enables virtual pins for the sum output. All right, so let's jump into Quartus and actually do the timing optimization of this add tree example. So you'll see I have Quartus open here. I have the add tree project open. I've already compiled it to save some time, but you'll notice there are some problems here we have to deal with. First of all, let's take a look at what we have included in this project. So we have the System Verilog file for the adder tree that we've been working with, and we have the SDC file which contains our clock constraint. All right, now if we look at what happened after we compiled, you'll notice down here there's an error saying timing requirements were not met. And up here in the compilation report, we see that the timing analyzer is highlighted in red. That means something bad happened. So let's expand this and take a look. So right here, we see some things in red. What these are is kind of different variations, different models of the FPGA we're working with. So you have different speed grades, and so here you have kind of a slow and fast model. You also have different operating conditions, so different temperatures. So this would be a high temperature model, these would be low temperature models. And you'll see two of the three models are red because they did not meet all the timing constraints. So if we look at the worst case model, which would be the slow high temperature model, we see that its Fmax is 146 megahertz. So this means Quartus was not able to achieve the 200 megahertz clock that we were requesting. It could only do 146 megahertz, which is considerably less than that. And if we look at the setup summary, we see we have a negative setup slack of negative 1.8 nanoseconds, and our total negative slack is negative 19 nanoseconds. So we have some work to do to fix this. If we look at the slow low temperature model, its Fmax is slightly faster. It's 157 megahertz, but it's still not that close to meeting our 200 megahertz clock constraint. Now, the fast low temperature model here did actually meet the constraint. And you may be wondering, well, why don't you just always check the worst case scenario? Well, you would likely do that if all you ever cared about was setup times. But remember, you can also have hold violations. And so if you had a faster FPGA, you could theoretically have hold violations that wouldn't occur in the slower FPGA. Now, that's not super common, but you still have to check all three because the slow ones, in rare cases, can meet all timing constraints and the fast ones may not. It's not common, but it can happen. And this multi-corner timing analysis basically analyzes all of them and gives you kind of the worst case situation across all the models. But the vast majority of the time, probably all you're going to care about is the slowest high temperature model, which is what we're going to look at today. All right, so we now know we didn't meet our clock. But now we need to figure out why we didn't meet that clock constraint. So what we can do is expand this timing analysis section here and double click the timing analyzer. All right, so here we have the timing analyzer open. And what we're going to do is come down here and double click the report setup summary. Now this is going to give us information on our clock signal for this slow high temperature model. So this is the information we saw earlier. But now we're going to right click it and go to report timing. And here you'll probably just want to accept the defaults. What you might want to change is the number of paths that get reported. So here we have a total negative slack of negative 19 nanoseconds. So we probably have maybe tens of failing paths. If this was a negative 100, you'd probably have a lot more paths that are failing. And so if you want to analyze those all at the same time, you would probably want to increase this number. But we're just going to leave it at the default of 10 and click report timing. Now this pops up with this information here. At the top, we have the top 10 worst failing paths in order of negative slack. So the top one here is essentially the critical path. It has the worst negative slack in the entire design. And you can see it's going from one of the input registers to the sum register, which is what we would expect to see because those were the inputs and outputs in our design. Now, if we come down here, let's just analyze this top path. If we look at the information down here, we can kind of get an idea of what's going on. So here we have the launch clock, and that was basically the clock for the source flip-flop, so the input registers in this case. We have the latch clock, that is the destination flip-flop clock, so that would be the sum register clock. You see that there's a 5 nanosecond difference between them because we want to be able to run at 200 megahertz. Now, where this gets a little confusing is you have to remember that when the launch clock has a rising clock edge, it doesn't immediately get to the source register. And so there's this clock delay down here of 2.672 nanoseconds. So at this point in time right here, this is when our source register, in this case, this input register right here, this is when it receives the rising edge of the launch clock. And then after that, we have the clock to Q output, or what Intel calls the micro clock to output time. And then we have all of the data delays of going through all the adders and all the interconnect delays. And that's what this 7.237 nanoseconds is. So basically, if we take the clock delay, this is when the clock arrives at the source flip-flop. A little bit of time later, we have the clock to Q output. So the data is coming out of the source register. And then we have all the other delays for the interconnect and adders. And at this point in time over here is when the data actually arrives at the destination flip-flop. Now we can see there's a problem because if we look down here, the data required time is right here. So we have a setup violation because our data arrival time is right here. Our data required time is over here. And so we have this negative slack of negative 1.828 nanoseconds. Now let's take a quick look at the data required time just so we understand why it is what it is, because it's a little confusing. So the latch clock starts right here. So 5 nanoseconds after the launch clock. But just like how the source clock had a delay of, or how the clock had a delay of getting to the source flip-flop, we have the same issue with the clock having a delay to get to the destination flip-flop. So that is this clock delay down here. So the latch edge starts right here. This is basically the rising edge for the destination flip-flop for the cycle that we are interested in. But it takes 3.066 nanoseconds before that rising clock edge actually arrives at our destination flip-flop, in this case, the sum register. And then on top of that, there's this setup time down here. Intel calls it the micro setup time, but it's not micro, it's negative 0.014 nanoseconds. So basically, we subtract a little bit of time from this clock delay, and that gives us this data required time. So this is just a graphical illustration of the equations I showed in the corresponding slides that we just looked at. So basically, this right here is the amount that we care about. That is the slack, the negative slack that we have to optimize away so that our data arrival time shows up on the left-hand side of the data required time. All right, so how do we figure out what the problem is? There's a bunch of different ways you can look at this. If you come over here, this gives you a summary of various statistics. So down here, we have information on the required path. There's not really anything we can do about the required path, so let's ignore that. The arrival path is what we care about. So this is the clock delay portion of it. Again, there's not much we can really do about that, so let's minimize that. So all of our effort is going to be spent on minimizing the data delays. That was the cell and interconnect delays between these two flip-flops. And if we look at this, we see that there are 16 interconnect delays. That's what the IC stands for. There are 17 cell delays. And then there's the one clock to Q, or their micro clock to output time. But that's a pretty tiny percentage of the time. In fact, if you look at this column right here, this shows you that 61% of this data delay comes from cell delays. 36 of it is interconnect delays, so that's not negligible. But still, our biggest bottleneck is this cell delay. And now we can actually take a very detailed look at exactly what is along that path. So if we come up here and look at the data arrival path, so I minimized the clock path because, again, we don't really care about that right now. We can actually step through kind of every single hop between these flip-flops inside of the FPGA. So right here, we basically see that the first delay is the clock to Q output time from this input flip-flop. So it takes 0.2 nanoseconds for the output to show up coming out of this flip-flop on the rising clock edge. You'll notice, though, that this right here is basically the total delay that's been incurred, and it doesn't start at 0. It starts at whatever the time was that it took the clock to arrive at the source flip-flop. And so that was 2.672 nanoseconds. If we add the 0.2 nanoseconds from this clock to Q output, we're now at 2.89 total nanoseconds of delay. After that, we have a cell delay, then an interconnect delay, then a cell delay, then an interconnect delay, and that iterates or repeats quite a bit until we get to the very end. And if you look over here, you can kind of see these signal names of what this corresponds to in our original code. Now, this is sometimes hard to interpret because Quartus will mangle the names, but we can kind of see what's going on here. We have our input registers. We have our add 0, so that was the first row of adders where we were adding the 4 pairs of 8 inputs. Here we have add 1, that was the second row of adders. Down here we have sum, which is also doing an add, so that's the final add, and then it goes into our output register. And so if we wanted to, we could step through this and see that, all right, so this interconnect delay added 0.9 nanoseconds. Then the first cell adds 0.58 nanoseconds. The next cell adds 0.061, and so on. But that's kind of tedious to figure out what's going on there. What you can do is, if you just want a graphical representation of what's going on, you can come up here to Locate Path and Locate in Technology Map Viewer. So this now gives us a graphical representation of, this is our source flip-flop, this is our destination flip-flop, and these are all of the resources that have to propagate, the signal has to propagate through to get from the source to the destination. And it's probably too small to read, so let me zoom in a little bit. So here's our input register, of this one particular flip-flop of the input register. And then we're going into a logic cell, which is basically a lookup table for this adder. And you'll notice there's a whole bunch of those for the same adder. And if we scroll over, still adders, still adders, still adders, still adders. Basically, these are all lookup tables that are being used to implement the adder tree that we saw. So it's basically going through each individual adder using a ripple carry adder. That's why you see multiple cells here for the same adder. It is then going through all three of the rows of the adder tree, and it is that long sequence of combinational logic that is creating our bottleneck. Alright, so now we've gone through the timing analyzer and saw that the original 200 megahertz clock constraint was violated by our original design. And we saw that the biggest bottleneck was due to logic or cell delays that resulted from a long combinational logic delay between all of the adders. So how do we go about optimizing this? Well, if you remember from the previous presentations, one common way of reducing logic delays is through pipelining. So let's go ahead and try that. To pipeline this design, we can just add a register after every adder. So in this case, the logic delay should never be more than one adder, which means it should be about 1/3 of the previous delay. Of course, this improvement doesn't come for free. We are really trading off latency and increased flip-flop usage in the FPGA to reduce logic delays, but that is very often an attractive trade-off for many applications. So this slide takes a look at how we revised the code to achieve this pipelining. Basically, we collapsed the two always blocks from the original code into a single always flip-flop block, and we can do this because every add operation is now followed by a register. So simply by assigning add operations to a logic variable on a rising clock edge, we are now creating the registers that we want on the output of each adder. You might notice that the final adder is coded slightly differently using a blocking assignment. Well, we do this because we don't accidentally want to create two registers on the sum output. Alright, so now let's jump back into the timing analyzer and see how things have improved with this pipelining. Alright, so here we are back in Quartus, but now we are using our optimized pipelined version of the adder tree. And I've already compiled this, and you can see something significantly different in the compilation report. So under the timing analyzer section, previously we saw basically that two of these three models did not meet timing constraints, and now all three of them do. So let's take a look at the worst case one, the slow high temperature model. And if we look at its Fmax, it's almost 240 megahertz now. So our clock constraint was 200 megahertz. So we are well above that, and we are considerably above what our original clock frequency was. So this is a massive improvement in frequency just by adding registers to the outputs of our adders. Now, really quickly, let's jump into the timing analyzer and just see how things look differently than the previous example, the unoptimized code. All right, so we're going to go through the same steps as before. So this is no longer red because we have a positive slack, and the total negative slack is 0 because we have no timing constraints. That's exactly what we wanted to see. All right, so we report the timing. All of these are now black instead of red. That's because they all have positive slack. If we look at the waveform view down here, we see something significantly different. So now our data arrival time is right here, and our data required time is over here. So our optimization, by pipelining the adders, we basically moved the data arrival time to the left of the data required time, which is exactly what was needed. So this green arrow here shows that we now have a positive slack. Similarly, if we go over here and look at the statistics, so previously we focused on these data delays on the arrival path, and in the original version of the code, the cell delays were the biggest bottleneck. And so by pipelining the adders, we significantly reduced those cell delays. And you'll see now that interconnect delays are actually the biggest contributor to the propagation delay between the registers. And if we needed to improve the clock frequency further, we could look into additional optimizations now for both the interconnect and the cell delays, but we don't need to do that for this example because we're well above our constraint of 200 megahertz. So that is it for this talk. In later examples, we will look at different types of optimizations, and thank you for watching.